All right. Hello, everyone. Welcome to the last lecture of the Battlecode lecture series. Today, we'll be talking about advanced topics, which you'll soon find out what it means. And it will be given by me and the great Jerry that I'm sure most of you guys have already met. All right. So today's topic is actually going to be bytecode hacking. And essentially, as you guys are all aware at this point, the entire Battlecode game world revolves around using your computational resources efficiently and doing everything that you want to get done. So in doing so, you'll inevitably come into contact with bytecodes and bytecode costs and how much bytecode you get to use. So today we're just gonna go over some tips and tricks on how to most efficiently use the computational resources that we have provided you. So as an overview of bytecode in Battlecode, this basically happens because we want to guarantee that we have equal resources allocated to both of the teams. In a sense, we want to make sure that the game is fair. And if we just do something simple like, oh, you have 10 seconds of runtime per robot, then because of how, what if your computer was actually running some other thing that essentially takes up some of the RAM resources, then essentially it's not deterministic and it's not exactly fair. And similarly, if you just use runtime, then it's not deterministic and it's going to be really difficult for people to debug their code, because if you run your robot multiple times and every time it does something different, then that's very difficult. So because of these reasons, we limit computation by using bytecode. And it's basically because bytecode is computable, it's deterministic, and then it also kind of roughly corresponds to computation power. So and for these reasons, we use bytecode counting in Battlecode. And basically the problem is bytecode limits in Battlecode are usually pretty low. I guess for reference, if you run a A-star search in a 10 by 10 grid, then that's basically will use up all of the bytecode computation that we allocate to a robot in a single turn. However, the maps in Battlecode are much larger, can go up to 60 by 60. So if you want to do something that encompasses the entire grid, you want to run some algorithm or pathfinding on it, you will not have enough bytecode. So being able to use your bytecode efficiently is going to be something that is very important. So today's lecture goes, we're going to go over how bytecode counting works and how exactly the engine does this and how exactly we measure how much bytecode you use. And then because of this, we're going to give you a quick introduction to some bytecode optimization techniques that you can use in order to make your code do more things in the same amount of bytecode. So we're going to start with some JVM Bytecode Basics. So JVM basically uses a stack-based architecture. If you're not familiar with this, feel free to ignore, I guess. But basically, it has a pretty comprehensive instruction set. When you compile your Java code, it generates the .class files, and it'll have a lot of different instructions that you won't see in your Java code, because Java is a high-level coding language. And once it's compiled down to this instruction set is fairly comprehensive. It can manipulate both primitives and objects, which might be different from some other disassemble languages that you guys are familiar with. If you're familiar with assembly or something, they're much more simple. So the JVM instruction set is much more comprehensive. It can do a lot of things. And a bytecode inside the JVM is basically an atomic instruction. So what an atomic instruction means is it's one instruction that will always be executed together. You can't split it up into multiple parts. You can't it won't ever be true where half the instruction got executed and the other half did not. So that's basically what being an atomic instruction means. And a bytecode is roughly equivalent to a single assembly instruction in native code. If you guys know what assembly is. Assembly is what C compiles into. And then bytecodes are also stored as a stream within the compiled java.class file. So you will have a stream or a list of bytecodes inside the .class file, which is basically what the code execution we're going to go through. And then when it's executed, it's executed within the context of a stack frame, which I'm going to talk a little bit more in the next slide. So if this just goes over your head, then I guess it's not super important. But for those of you that are familiar with stack-based architectures, this is basically the basics of how bytecode works inside the JVM. So a stack frame is kind of like a code execution environment, I guess. And so you see in this diagram over here, there's an execution stack. So this is basically stack-based architecture. When the code is running, it will push frames onto the stack and it will execute them in the execution order. And for each frame contains an operand stack, which is kind of a bunch of, I don't know, variables, things it's using. And then it also has an array of local variables, and then also a reference to a constant pool of the class of the current method. So basically, it will have the local variables kind of copied, or the reference is copied inside this frame specifically, so it's easy to access. And then the operands, which is like if you call a function, then it'll be like operands that you're calling it with. And then it's also pointing to the constant pool, which is the class data that might be like outside this specific frame that it can also access. So this kind of will be somewhat related to, how you might optimize bytecode usage later. But yeah, this is basically kind of how stack frames work inside the JVM. So now, Jerry, I would like you to demonstrate compiling a simple Java file into the .class file, and then we can like take a look at the bytecode instructions that it compiles into.
All right, yes, so I'm going to do a quick demo. The reason we do a demo is because it's really easy to say a lot of things about what bytecodes do or like how much bytecode you're using, but it's sort of really hard to actually know what we're talking about without actually seeing some bytecodes happen. So what we're going to do is we're going to take a simple program on the left, which it just computes the discriminant of a quadratic equation. And what we're going to do is we're going to actually take a peek at the bytecodes in this program and sort of get a feel for what's actually going on, what Java is actually doing. So we have a program like this. The first thing we're going to do is we're going to compile it just like we would do for any excuse me while I set up my environment there. That puts me in Java 8. But the first thing we're going to do is we're going to compile this Java code. So we're going to Java C this quadratic formula of Java. So once that compiles, what we're going to actually do is going to take a peek at the bytecode. So first, I'm just going to convince you that this code actually does what I said it does. So if I said we had a quadratic equation, so say x squared plus 2x plus 1 is 0. This is a perfect square, so the discriminant of that is a 0. If we add on some extra, then that actually is completely above the x-axis, so we have a negative discriminant. We take some off, then this is always below. This dips below the x-axis on points. At some point, we have two real roots. We have the positive discriminant, but that's just to convince you that this code works. But now let's actually look at what is going on below the hood. So Java ships with this cool command called Java P. So you've probably used Java C to compile your code. You've used Java to run your code. You use Java P to take a look around inside. You use Java P-C quadratic formula. And this actually takes our code and it dumps out a lot of stuff. It's a lot of scary looking stuff that we may not have really seen before, but let's take a look at what's actually happening. So this just says we have a class quadratic formula, and inside this quadratic formula class, it's detected that there's a couple of methods. We have like the main method, we have the discriminant method, which we've all defined before. There's also another method that is added as well, the constructor method for the quadratic formula. So this is just sort of, if you're not familiar with constructors, you don't have to worry about it, but you can think of it as just like what happens when you create a new quadratic formula object. So there, like you can imagine that quadratic formula is a class. There is definitely nothing wrong with stopping you saying from, like there's nothing stopping you from saying quadratic formula X is new quadratic formula. Like you can definitely do that, and Java will be completely happy with you doing that. And so that's just the code that gets run if you do try to create a quadratic formula. But the exciting thing that's happening here is, and the stuff we'll look the most at, is what's actually happening in the discriminant function, the discriminant method all the way down here, because we'll actually just pick this apart to get a sense of just what sort of level of computation we're dealing with bytecodes. So you can see that just a very simple one line piece of code, b squared minus 4ac, very, very simple line of code, actually got broken up into many lines of code here. So let's actually try to take a look at what's happening. So, whoops, that's not the button I wanted to press. Let's remove that and come back to that. I'll just type it down at the bottom. Cool. So the deal with what's happening down here is we have the discriminant method, and it's taking in these three parameters. We have the three parameters, which are A, B, and C. Three of them are the three integers that we're receiving here. So once these parameters are received, they actually turn into local variables to this method. So these parameters are local variables to this method. They can't be accessed anywhere outside the method, and you can access them from anywhere inside the method. So they are local variables. And so you can imagine, so you might remember from before on the slide, you talked about having an array of local variables. So you can imagine this array having, you could imagine it as something like as an int array. So local variable array is like a new array of integers containing that A, B, and C. Right. So we have this array containing A, B, and C. These are local variables. And now, so the sort of things that Java will actually do when it tries to compute b squared minus 4ac sort of look like this. The first thing it's going to do actually is it's going to load. So that I load there, what it's actually going to do is it's actually getting the first element of your local variable array. And we're saying first as local variable array indexed by 1. So it's first according to sort of like the zero-based indexing that Java uses. In natural English, this is the second element. So we're actually loading the value of b. We're loading the value of b. And the reason we load it twice is because what multiplication does. So the second command we see, so the second bytecode says imul. And what imul says is we're going to take the last two numbers that we loaded, and then we're going to unload them, multiply them, and then load the product. I'm going to take the last two numbers we loaded, unload them, multiply them, and then load the product back on. So now, after this, now we've, I don't know how to draw arrows. Okay, I'll just deal with that big red annoying color. But we're going to load that product, and then now we've only got the value of b squared loaded, right? So we've loaded b twice, right? So we've loaded b twice with that iload1, and then we hit the imul, which unloads the two b's, multiplies them, and then puts b squared on the list of things we've loaded. All right, so we're going to come back. We're going to come back to that. We've got b squared loaded. The third thing says iconst 4. So even whenever you just pick a number, just writing the number 4 actually costs you a bytecode. It costs you a bytecode just to write the number 4. Because as you can see here, the third line, iconst 4, actually says load the number 4. It actually means load the number 4. And then iload 0 we've seen before. Iload 0 means we're just going to load the first thing in our local variable array. So we're loading the value of a, because that's the first thing in there. And then the imul is again going to do a multiplication. So it's going to take the 4 and the a, because those are the last two things we've done. We're going to unload them, multiply them, and then load the product. So now we've loaded, the b squared is always still there. And then we loaded 4, we loaded a, and then we unloaded them and then replaced them with a product. So that's b squared, and now I got 4a over there. Okay, so that's the imul done. And now we're going to iload 2, which is going to load that c. So that's the second thing in our local variable array. Now imul is going to say, imul is going to take, we had b squared, we had 4a, we loaded the c, but then the imul is going to take the 4a and that c, and it's going to replace it with 4ac. And finally, we have isub, which does, not so surprisingly, it's going to do exactly the same thing as imul, except with subtraction instead of multiplication. So it's going to take the last two things, subtract them, and then replace them onto the list of stuff we've loaded. So now it's going to take the loaded, we're going to take the b squared and the 4ac, and it's going to take the subtraction. So now we've actually got b squared minus 4ac. And then finally, that I return returns the last thing we've loaded. That gives us the b squared minus 4ac. So surprisingly, just a simple command, simple line of code, b squared, return b squared minus 4ac, actually compiles into 10 bytecodes here. That actually compiles into 10 bytecodes. So as you can see, bytecodes, you can actually spend them very easily. They're very easy to spend. You can write a very simple line of code and then they just disappear. But I guess that's sort of the point of today's lecture, how to do some sort of simple tricks you can do to make your bytecodes sort of get a bit more power out of your bytecodes. So that's sort of just a demo for now, and we'll come back to some more demos in a bit. So I'll pass it back to Elizabeth.
All right, I'm gonna steal the screen sharing again. So thank you, Jerry, for your generous demonstration. So now that you guys have had a little deeper dive into how bytecodes work, we're going to talk about how bytecode and battlecode works in a little bit more detail. So basically how the engine does this is before your code executes, the engine will like scan through your entire like generated program tree, and then we'll compute the bytecode cost of like each basic block. For those of you guys that don't know what a basic block is, you can just think of like a chunk of code that will always execute together. So if you have like a function call, then like if you have like a large chunk of code and then inside it there's a function call, then that function call is like its own basic block, because it will like always execute together. So you can just think of like chunks of code. So we compute the bytecode cost of like each chunk of code within your like generated program tree. And then at like the end of each chunk of code, we're gonna inject like a checkpoint that says like, oh, this chunk of code is gonna be like this much bytecode. Like every time you run this chunk of code, you're gonna use this much bytecode. And these like basic blocks or chunks of code are basically like divided so that there's no like branching or function calling. So it'll always have like the same bytecode cost. So that's why we can like mark each chunk of code with like this bytecode cost. And then when your code is actually run and we're actually executing these basic blocks, while they're executing, we'll increment the robot's internal bytecode counter with like the basic blocks that execute and like how much bytecode each of those basic blocks uses. And then if at any given point we're like incrementing this bytecode counter and the running tally of like the total bytecode used exceeds the bytecode limit that we allocate you, then the robot execution is halted immediately and then the execution of the next robot begins. So essentially, if you ever go past the bytecode that we allocate you, then your turn to skip. And it's not like every single line of code we like check your bytecode. So it's not the exact line of code where you run out of bytecode that we like stop your robot's execution. It'll be like that basic block, which will basically like functionally it will be like something that has to work together. So that's basically how it works. And then a thing you can notice is that you're only penalized for the total number of bytecodes you use. You're not penalized for like, how many bytecodes each specific line uses, or, like how many function calls you're making, or yada, yada, or like how long your code runs. Like we're not penalizing you for having very inefficient, long runtime codes. You're only penalized for a number of bytecodes you use. So these are some things to keep in mind if you want to optimize your code's bytecode usage. So the first thing you'll know is that size doesn't matter. So here's an example, loading some variables into your stack frame execution. So in the left column, you have this iload 0, which is a 1 byte special compact instruction. So this instruction only takes 1 byte. It's very compact and it's special. It basically loads the first local variable 0, which Jerry already demonstrated in his little compilation example. And on the right side, this iload without like the _0, it's basically loading a specific argument, which is the argument represented by hex code 05. And this instruction is a 2-byte instruction. So as you can see, the numbers that have like colons following them, this is 01 and this one is 02 because it's basically counting the number of bytes that these instructions take up. However, the size of the instruction actually doesn't matter. The only thing that matters is the number of bytecodes that you're using. So in both of these scenarios, you have used 2 bytecodes, even though in the first scenario you only used 2 bytes for these bytecodes, and then the second one used 3 bytes because the first instruction was actually 2 bytes. So this basically, if you can, use bigger instructions and like save bytecodes, then go for it. And then the second thing is that complexity doesn't matter. It doesn't matter how complicated your code is or like how simple your code is if it uses a lot of bytecodes. So this is basically someone asked the question earlier, like are if else's, are both the if and the else like counted even though you only execute one of them? So here the biggest example of complexity not mattering is basically switch statements. Even though it does the exact same thing as if else statements, it uses like way less bytecodes. And Jerry has a second demonstration with the compilation to show you why bytecode wise switch statements are so much more efficient.
All right, time for another demo. So this demo is a bit of a longer one in terms of the amount of code we've got here. It does something pretty cool though. I sort of like this little mini calculator. So let's compile this calculator and just play with it for a little bit first. So let's compile this calculator.java. So we've got this calculator compiled. Let's just run it to see what it does. So let's actually just take a look at it. It actually just runs in an infinite loop. It repeatedly asks you for a mathematical operation and an input number. And what it's actually going to do is it's going to take the current value, which starts off as 0, and then actually just combine that with your mathematical operation. So the easiest way to see it is if we gave it, for example, plus as the operation, so it's going to read in, so fin.next, so is our input, it's going to read in the operation as plus, and then we told it to say plus 8 as the input. So if the input is 8, then it's going to get compute next value using the operation of plus, using the current value of 0, and the input of 8. So in other words, we're actually just going to compute A op B. So this function computes compute A op B, where in this case we have A is 0, op is plus, and B is 8. So unsurprisingly, the current value is now 8. And so we can play with this. We can do like 8 times 3, and then we get 24. We can do 24 divided by 6. We now have 4. 4 times 17 is whatever that is. You can keep on playing with that. As a way to get out of the while true, you could either say kill your code, or if you're evil and nasty like me, you could force it to divide by 0. So 2 ways of getting out of that code, but that's sort of not what we're going to be focusing on. The thing we're going to focus on is this implementation of compute next value. So this compute next value, which takes in the operation and then combines A and B. So if it's a plus, we're going to do the A plus B. If it's a minus, we're going to do A minus B. If it's a times, we're going to do A times B. Divide, we're going to do division. If we don't know what it is, then we just pretend that the user didn't know what they were doing and ignore it. But let's do the same thing as before. We're going to Java P -c the calculator. Right, so in Java P -c the calculator. All right, so we have compute next value 1. And this is all the bytecode that compute next value 1 contains. So again, we're going to skip over the main. So the main contains a lot of crazy nonsense to sort of like handle the scanner and also the printing and all of like this string magic here. So we're going to skip over that, but we're going to focus on the compute next value 1 here, which is where a lot of the work is happening. So what we'll actually look at is actually what's happening here. So first thing that's happening is iload 0. Iload 0 is something we are familiar with. So iload 0, we're going to like load the operation. We're going to load the operation. Now, after we load the operation, we have this bi push. So bi push, we actually if we just quickly go into Python, the character 43 is a plus. So what we're actually doing is bi push is sort of like the const before, where we take a constant, but this time we're dealing with just a single byte, so a smaller constant. So we're actually taking the number 43, and we're also pushing the number 43. Okay. So now that we have 2 numbers, we have the operation loaded, and we've loaded the plus. So we've loaded the 43. So we've loaded the operation, we've loaded 43. And now what we're going to do is we're going to do an if statement. Now this if statement is saying we're going to say if, we're going to be comparing the last 2 numbers we've loaded, and the NE stands for not equal. So we're going to be comparing them, and we're going to say if they're not equal. So we're going to compare the last 2 numbers we've loaded, and if they're not equal, we're going to jump. We're going to jump to location 10. In other words, we're going to skip everything. We're going to go directly to location 10 and skip everything else in between. On the other hand, like if they were not equal, then we're going to not do the skip. So in other words, if they were equal, we're going to just continue running this code normally. Right. So if they were equal, we're just going to go, we would then run to line 6, where we're going to get A and B. We're going to do the add of A and B and then return. Right. So sort of like the 6 through 9 is sort of like the familiar, hopefully familiar addition code, where so we're loading A and B, we're adding them and returning that result. So essentially, so what we've seen so far is line 3 is doing a comparison. We're saying is the operation equal to 43? Because if it's 43, then it's a plus. If it is equal, then continue. If it's not equal, then jump to location 10, because we don't want to run the next few lines of code. So that's what this code is saying. So the 2 things we want to notice about this code are, firstly, most of the time when you run this code, not every bytecode you see here is going to get run. For example, if the operation was a plus, we'll actually just get here, and then everything from 10 onwards never gets run at all. As another example, if the operation was a minus, we'll jump to 10 because the first check failed. And then we're going to compare it again with 45. And the 45, if you actually check it, is the minus. So you're going to check it. You're going to check, okay, so it is 45. And now we're going to run 16 through 19, which loads A and B and does the subtraction. So that's sort of what's happening here. But the key thing is not every bytecode here gets run. So the first thing I want to point out is that Battlecode charges the number of bytecodes you run, not the number of bytecodes that are written. What this means is, firstly, if you have an if statement or an else if statement or something like that, you're not charged for all of them. You're only charged for the one that actually ends up running. But on the flip side, if you have a loop, then every time that loop runs, you're going to get charged again. So if you have a loop containing just a single bytecode, but that bytecode gets run 100 times, you'll get charged for 100 bytecode instead of just one. So you're going to get charged for every bytecode that gets run. So given that, the second thing, we're going to say is that we should also notice that, so the second thing we're going to say is that this is actually sort of inefficient. And it's kind of inefficient because we're comparing the same value. We're comparing just like the value of up. So like after we iLoad 0, we're comparing it many, many times. And it's sort of like the same way every time. Like if you think about what's happening here, we're loading we're loading 0, so we're loading the operation, and then we're going to load a 43, and then we're going to do a check. If the check fails, then we're going to load it again, load a 45, and do a check. If that check fails, we're going to load it again, load a 42, and do a check. And if that also fails, then we're going to have to again do a load a 47, and then compare it again. So in fact, if every single time this function got called, I ask you to do a division, then you would have to do many, many extra bytecode every single time. Because every single time you run this function, every check you run will get charged, right? So like it's not like you only get charged once for just comparing the operation. Right? Every time you try to inspect what the value of operation is, you're actually charged something like 3 bytecode, because you have to load the operation, you have to load what it's getting compared to, and then you have to run the if I compare not equal bytecode. So that is a lot of bytecode to be spending just to determine which type of operation it is. Like that is, if you just got a single division operation, you're actually spending something like 12 bytecodes on comparisons, and then the remaining 4 on just doing the actual division. So that's actually a lot of bytecodes you're spending. So it would be great if there was actually a way for us to make this better. And so what we're going to do is we're going to take a quick look at switch statements. So switch statements are a really useful thing to do when sort of you're comparing the same thing multiple times. We've actually seen switch statements already. We actually saw them all the way at the start in our first example funcs player, where you might remember all the way at the start of the run method, like the public static void run, we had the switch statement around the type of the robot. You were switching on the type of the robot. And that's exactly what we're going to do here as well. So I'm going to remove all this extra blank space and actually enable this code. I'm going to replace compute next value 1 with version 2. So just take a moment to stare at this code, convince yourself that it does exactly the same thing. So we're just checking what is the operation, and then just do what the operation says. But if we run this, so let's recompile that. And then let's take a look at the bytecode. So compute next value 1 is still here. So that's still here if we want to take a look at it. But now let's take a look at what compute next value 2 does. So first, we're still going to do the same thing. We're going to load 0. I'm going to load that operation. But the next thing that's going to happen is we're going to do something called a table switch. And what a table switch says is we're actually going to take a look at what the contents were of the last thing we loaded. And then depending on what it was, we're going to jump to somewhere different. So we're going to go to a different location in the bytecode, depending on what the value was that we just loaded. So in particular, what it's saying is, well, okay, if we loaded, say, a 42, I think 42 is the I think 42 is the asterisk for multiplication. If we loaded a 42 for an asterisk, then we're going to jump to location 48. And then at 48, we're going to load the two numbers and then do a multiplication and return. If we loaded a 43, we're going to do a jump to 40 because the 43 is, we're going to jump to location 40 because the 43 is the plus symbol. So we're going to load the two numbers, we're going to do the addition and return. We loaded a 44, we're going to jump to 56 because that is, I believe, the, I actually think, yeah, so 56 is a case where we don't actually know what it is. 56 is the nonsense case. But 45 goes to 44, which is then our subtraction case. So 44, it starts here, we're doing subtraction. 46 also goes to nonsense, and 47 goes to, I think that is division. 52 is division. All right, and then so this is the same code. Like most of this stuff down here is the same, but it's now missing that complete, we now no longer have several calls to iLoad 0. We only have to load the operation once because this switch command, this table switch, is going to just look at the load 0 once and then send us to the correct location. So we don't actually have to do loads or any string of comparisons at all. So the first thing to notice is that the overall number down the bottom here, 57, is greater than the 41 we had before. The 57 is greater than the 41 we had before. Does that mean that using a switch is actually worse than just repeated if-else's? Like we've managed to go all the way down to 57, which is a much bigger number. All right, that's actually a good question. Let's leave it in the chat. What do you think? Do you think that the 57 is worse than the 41? And Elizabeth, do you want to tell me what everyone thinks? Or is it just a wall of silence?
I don't know what other people think.
Is there anything happening in chat?
No, I don't think so. There was someone asking questions about if-else's, and I answered it earlier, but you just talked about it too.
Oh dear. Okay. Well, hopefully this is still making sense. If there's any questions, you should definitely ask. But the answer to this hypothetical question is that the 57, even though it's a bigger number, is actually not at all worse than a 41. In fact, this new version of the function is a lot better than what we had before. And the reason is that for this is a couple of things. The first thing I have to emphasize again is two things. So the first thing I have to emphasize is that the 57, or the numbers you see down the side here, are like the byte offset. So it's a number of bytes that these instructions are occupying, or like the location in your code that they are. And remember from before that the size of the bytecode doesn't matter. So even though the previous one was only 41 and this one is now 57, we don't actually care that it's bigger. Whether or not it's actually bigger doesn't actually change, it's not what we're directly measuring. So you should never actually look directly at the numbers on the side. What you want to do instead is look at the number of bytecodes. But even that being said, the second thing I have to mention is, again, we're not actually counting the number of bytecodes that exist in your code. We're counting the number of bytecodes that you actually end up running. So in this case, if we actually count the number of bytecodes we run, it's almost always the same. Like no matter what operation you put in, we're going to load the operation. We're going to do a single switch, which is going to send us somewhere, for example here, where we're going to then load two numbers, do a multiplication, and return. And that's all that will ever happen. So it's one load, one switch, two more loads, a multiplication, and a return. So that's essentially, this method is now always going to take 6 bytecodes and no more. And this is a pretty big improvement over what we had before, especially if we had to do division, where you would go down one by one and hit every single comparison. In fact, even in the add case, where right at the start, our add case used to be 1, 2, 3, 4, 5, 6, 7 operations. So it turns out that no matter what the input was, this is actually always an improvement. So the moral of the story here is, if you can use a switch statement, chances are, and you should check this for yourself as well though, but chances are switch statements in a lot of cases can probably do you a good favor in your code in terms of like reducing the number of bytecodes that you end up using. And so a note that I do want to throw in here is that when you are writing code, it is definitely possible to actually do the same check on your own code. So if you have a repo like this, so this is our lecture player repo again. So if you go in, so after you do your build, so you'll know that, like, as usual, we have all of our code living in the source directory. But after you actually do like the Gradle build task or something, it actually creates a build directory. So there's a build directory, so a build folder. And so inside this build folder, you can go into classes, you can go into your bot. So inside your build, so you can go into build classes / your bot. And then once you're here, you can do exactly the same thing. So you can do Java P -C, whichever thing you would like to take a look at. So for example, for us, we can take a look at robot player. And then that is the bytecode dump of robot player. So this is the bytecode dump of robot player. So there's a lot of code in here. And you can see that there is definitely a lot of bytecode in here. But this is essentially how you can do the same checks on your own code. So you can scroll through and find the functions that you are most interested in. You can see there's a switch in here as well. And this is the switch that corresponds to us. I think this is the one that corresponds to us switching on the type of the robot. So this is the switch in your in the robot player.run, which switches on the type of the robot. But that's it for this part of the demo. So I'll switch it back to Elizabeth again.
All right, thank you, Jerry, for your nice demonstration. Now we're gonna go back to the boring slides. All right, so basically our optimization goal when you're trying to optimize bytecode is just to reduce the total instruction count to as few as possible. And then we're gonna go over some very quick and easy examples on like how you might want to approach this. So I guess now that Jerry already showed you guys how to compile your code and then like actually see the bytecodes, when you're trying to like do things to optimize your bytecode count, just like, you know, compile it from time to time, check the bytecode, see if things are going down as you expected, and then you'll learn some other tips and tricks that you might be able to work with as well. So an example that we're going to work with is going to be a very simple loop. Let's say we have this thing where we're iterating over a bunch of robot infos that we're going to get, and then we're just going to call like a scan method, which can just be like anything you want to do. So this loop, this enhanced for loop, is 10 bytecodes per loop iteration. If you want to, you know, write it down yourself, decompile it, whatever, if you structure it, it will spit out 10 bytecodes per loop iteration. And then this other one, which is an optimized version, only has 9 bytecodes per loop iteration. So how does this happen? Basically, under the hood, these enhanced for loops in Java, although it's like very simple, convenient to write, and then they're really easy to read and make your code really like readable and easy to use. It has a lot of stuff under the hood. It basically converts it into one of these traditional for loops, and it has to store this extra variable r_info every single loop iteration. Like it has to, you know, load it into that variable, you know, use it, and then like, you know, store it, whatever. Which is an extra layer of loading, storing extra bytecodes that it's getting to use. It also has like the implicit loop index. So, you know, this optimized version having this variable I doesn't actually affect the bytecode counts as compared to the enhanced for loop because they both under the hood do the same thing. The array length, yada, yada. These are all things that both of these loops will have to use. So this old-fashioned loop actually saves the bytecode count by pre-computing length. So first of all, you don't have to try to query the length of this array every single iteration of the loop. And it also avoids loading and storing this variable r_info for each loop iteration. It actually uses an extra bytecode. What was it again? There was some reason why it uses like another extra bytecode. So basically it saves 2 bytecode and uses an extra bytecode. So overall it saves 1 bytecode per loop iteration. And if you actually run these different code segments, compile them, and you check the bytecode instructions that it spits out, you'll understand why this happens. So restructuring your loops to not use these like quick and easy ways that, you know, makes it under the hood use more computation power is one way you can use to save some a little bit more bytecode. So let's say we're just going to start with like this thing that has 10 bytecodes, and now we did a little bit of restructuring, a little bit of pre-computation, and now we're optimizing it down to 9 bytecodes per iteration. What else can we do? So now we take this optimized version and we're like, okay, how can we squeeze more bytecodes out of this? As you can see, all we did here, the difference is we copied this enemy robots array into a local array. And we didn't actually copy the array. We just copied the reference into a local variable. I guess this code comes out of like the assumption that, okay, if enemy robots was a class level variable, as in like, you know, you're like robot, you have like the class variables outside, and then this was like in some function, and then it was like using the class variables. Then if you make a local copy of the reference, it will actually save you bytecode every single loop iteration. And this is because the local variables are part of the stack frame in a JVM, and class variables are not. So if you go back to this picture here of the stack frame, see in each execution frame, it has its local variable array. So by creating a copy of the reference of the class variable, you're essentially like having a reference of it in this local variable array, which is like really easy to access. And if you're accessing like the class variables instead, you have to like go through a second step and like load it every single time that you want to use it. So that's why if you have this local variable reference, even though it looks like the exact same thing and looks like just an extra line of code, you're actually saving a bytecode every single loop iteration, because every single loop iteration, it tries to access this array. And then we save another bytecode every loop iteration. Yay. All right, anything else we can do? All right, so now we have 8 bytecodes every loop iteration. So now we can see, you can actually save more bytecodes by changing the for loop itself. And then instead of starting with I equals 0 and comparing it against length every single time and incrementing it, if you do it the other way around, where you start at length and then you decrement it every single time and then compare it against 0, you're actually saving bytecodes every single loop iteration. And how does this work? So basically, Java has a special bytecode for checking whether a value is equal to 0, which is IFGE, like if greater than equal to, like this stands for if greater than equal to, and implicitly it's like implying if greater than or equal to 0. I think there's also like a if less than equal to or something, but I'm not sure. So as Jerry's demonstration has showed, every time you're like comparing values, you're actually loading, you know, X, which you're like comparing against, and then you're loading like the value that you're comparing it. So if you're comparing X and Y, you have to load both X and Y and then compare them. So that's like 3 bytecodes. However, if instead of doing that, you're just comparing it against 0, then you don't need to load the 0, because 0 is a special value, and Java internally knows like it knows what 0 is. It knows the value of 0, so you don't have to load it every time you want to check against it. And therefore, by doing this, on having your loop index compare against 0 instead of comparing against this like arbitrary length value, you're basically avoiding pushing the number you're checking against onto the stack, and then you're saving 1 bytecode per iteration. So basically, we started with this chunk of code, and then we ended with this. And then from going from this one to this one, you actually also don't need to pre-compute length again, because you're only using it once. And then by doing this, you actually started with 10 bytecodes per loop iteration, and then you cut it down to 7 per loop iterations. And that is actually 30% of your bytecode cost. So that's quite significant. And this saves computation. You can now use it to do other things. Maybe you can run a few more steps of pathfinding in your like algorithm. Maybe you can, you know, do a little bit more calculations in like a targeting system on like who you want to hit as your robot. Is like attacking the enemy army, yada yada. So there's a lot of things you can do with these extra computation. And if this loop that you like save computation on runs for like hundreds or thousands of iterations, then you're actually saving a very non-trivial amount of bytecode. And then another thing that we're not going to go into details with is that Java has loop naming. So you can name your loops like very arbitrarily. And by that, you just put like some name and then colon, and then you write your loop. So I can do like loop 1 colon for I equals yada yada, and then you can have like nested loops. They're all named different things. And loop naming is good for saving bytecodes, because then you can just break out of arbitrary loops at arbitrary points in time. I believe this is not possible in Python. I actually learned Java before Python, so when I went to Python, I was really annoyed because I couldn't do it. So you can name your nested loops like all different names, and then at any given point in execution, you can cut out of like any one of the nested loops or continue any of the nested loops that you're trying to like access. And this saves a lot of bytecode, because you don't have to, you know, do the extra computation checks like every single time you're running through the loops. So that's something you guys can explore with, which I believe a lot of people will find it useful, because loop naming is nice and everyone uses nested loops, right? So what's next, Jerry? Any announcements?
All right, so great question. So what's next? So let's actually take the next slide. So this, as you may be aware, was this is the second week of Battlecode already, and we're already in the last lecture of our lecture series. So what we're going to do is spend a little bit of time talking about, well, as the title of the previous slide suggests, what's coming next down the line. So first of all, as this is sort of like the end of our formal lecture series, we sort of want to talk about a bit about sort of ideas for what you might like to do to consider where you want to take your bot from here. So we sort of, as a recap of what we did, we started out with a bit of an intro, so sort of like an introduction to the bot, introduction to Java, introduction to Git, sort of like things that you could do to sort of get up and running. And then we spend sort of like the next sort of section in our lecture series doing these series of incremental changes to the bot, right? So like we did things like, well, if you can see some lead as a reminder, why don't you walk towards it instead of going in a random direction, right? Like we did things such as, well, if you know that like that direction has lower passability, if that has lower rubble, then you should go in that direction because there is lower rubble over there. Sort of like we've done these series of small changes, a lot of small but impactful changes. And so, as I probably mentioned at some point over the last few lectures, I think the Battlecode is a lot about, well, how can you make these incremental changes pack the most punch for you? And how can you like sort of like get the most out of your time? Because in the end, I think there is so much you want to do in Battlecode, but there is only that much time that you have. So it's all about sort of like deciding which changes would you like to do next. And so something I would really encourage you to continue to think about going into the next 2 weeks, sort of as we head towards our larger tournaments, is, well, which other changes would you like to see in your bot? Do you see something, well, is your bot still falling back onto making random moves sometimes maybe? Or is it doing something where you think, well, maybe it could be making this one decision slightly better? And so continuing to make these incremental changes, just as we have been in the lecture series, as long as you can continue to make those changes, every single one of these will make a difference to your bot and make it like that much better. And then as time goes by, as you sort of like get more and more of these changes, your bot will definitely improve, and you will definitely see sort of a market improvement in your bot's performance. Another thing that I sort of want to mention that we sort of like, I think we've talked a bit less about, is sort of higher level strategies. So in terms of like how you want to strategize your bot in Battlecode, you might often, and sometimes in Elizabeth, you're screen sharing something. All right. Can we go back to the previous slide, please? All right, thanks. All right, where are we? So the second thing we haven't talked about in Battlecode is what you're gonna do with strategy. So there is the higher level types of strategy, and sort of like the higher level types of strategy are like, well, how you can manage your bot at a high level. Things like, well, do I want to create a bot that sort of creates a lot of attacking robots? Or do I want to create a bot that does a lot of defense? Or do I want to create a bot that does a lot of farming, that creates a lot of resource? Or do I want to go for something that does a bit of a mix? Or perhaps I want to do a bot that like is ready to do either of these, but sort of like makes a decision depending on the map it sees. So it really depends on sort of like, what do you see? Or like, what do you want to see your bot doing at a high level? And that's sort of like what we talk about when we talk about high level macro strategy. Sort of like, well, how do you want to make those big picture decisions on like a grand scale? But at the same time, perhaps you want to spend a bit more time also focusing on the detailed micro level strategy. So micro level strategy includes things like, well, how do you specifically do combat? Like if I have like a single soldier coming up against an opponent's soldier, do I attack it now? Do I wait one turn and then attack it? Because maybe that one turn will be better for me in terms of my cooldown. Do I walk towards it, or do I back off, or do I stay still? Because there's all of these micro level decisions that you can be making. And sort of like Battlecode has this interplay between, well, the macro strategy matters a lot, and the micro strategy also matters a lot. And so it's really worth thinking about as you make these incremental changes, whether each change sort of impacts your micro strategy or your macro strategy. And also think about sort of like how you want to drive the direction of your bot. And the third thing I want to mention is definitely just remember to keep on testing versions of your bot against each other. In case you haven't sort of like discovered the feature yet, you can have multiple folders. You can have multiple folders of your bot. You can have like example funcs player, which we give you. You can create another folder, also known as another directory or another package, containing another name of your bot, and then you can sort of like have lots of different folders. You can play your bots against each other and sort of like decide which one is your best bot to submit. And just keep in mind that when you do submit your bot, you submit the one that you know. When you do submit your bot, make sure you only submit that one alone, because I believe our scrimmage runner will actually check that you only submit one folder. But those are some notes on some ideas on things you might like to do on how to bot better. Definitely do a lot of testing, but also like definitely think about what you would like to see in your series of incremental changes. Could I also get the next slide, Elizabeth? Could I get the next slide? Awesome. So what's coming up next? So to be continued, things coming up are tournament-wise, we have the sprint tournament coming up very soon. So we're heading into the weekend, and on Tuesday, so the 18th, we will be running the second sprint tournament. So this is another opportunity to get a sense of what the new meta is like. And submissions for that will be due on the 17th. So that's the Monday at 7 p.m. Eastern. We will be we'll definitely be live streaming this one again, and there will again be a small prize available in the second sprint tournament. For heading into the bigger tournaments, our qualifying tournaments will begin for our US students. So if you're a fully US team, the qualifying tournament will be on the 25th, which is also a Tuesday, and the submissions for that will be due one day before, the Monday at 7 p.m. We have the full tournament calendar on our website, so if you want to check where all of the other tournaments will be. Keep in mind that there is a very large prize pool. So the prize pool is well above $30,000. And so as anomalies occur over time, that prize pool may sporadically increase in size. But the key things to note are that for the main tournament, we will be giving out prizes to the top 16 teams. And additionally, we have newbie tournament prizes to the top 2 MIT teams who have never competed in Battlecode before. At the same time, there are also bonus categories for question mark. I guess we'll find out what these bonus categories are. So these are the tournaments to be looking forward to. And so our final tournament itself, so the final tournament will be held on the Saturday, the 29th of January in Kresge, not in Kresge, it will be in 32123 in the Stata Center. So it'll be in 32123. So that's the final tournament on the 29th of January. And so this will be in person. We'll encourage all of you to come along, and if you're in the area, we definitely encourage you to come and participate or spectate the final tournament. We'll also have our amazing sponsors with us as well. And as a final thing to note is that if you're taking Battlecode for credit, so if you're a registered student in 6147, we will be releasing instructions for how to defeat the reference player and the strategy report on Canvas. We'll be releasing this early next week, and we'll be accepting submissions for this through to the end of the IAP period, which will be 11:59 on the 28th of January. So that's the Friday. But other than that, it has been a pleasure to join with you all over Twitch or on Discord. We'll definitely still be excited to meet you all on Discord. So best of luck in the competition. Definitely still hang out over Discord. Love to see you in person at the final tournament on the 29th in the Stata Center. So that being said, good luck, best of luck. It's been great getting to know all of you.
Bye-bye.